Now we'll talk about defects. I'm reminded of this story of this old guy. He went to church and he came home. And his wife asked him, "Well, how was church?" And he said, "Fine." He didn't say too much. And she said, "Well, what did he talk about?" And he said, "Sin." And she said, "Well, what did he say?" And he said, "He were again it." So, what are we talking about here? Defects. Well, what do we have to say about them? We're again them. Basically, we're going to start with some definitions of defects, having to do with defects, and you'll see a couple of different definitions here that I gleaned from the literature. And then we'll talk about three aspects of defects. Preventing defects, which is the best thing that you could do, right? But if you're not able to prevent a defect and it gets in there, then you have to find the defect. We already talked about that when we talked about reviews, if you recall. And then after you find a defect, you have to fix it. So we'll talk about what happens and what kinds of activities are involved in all three of those things: preventing, finding, and fixing defects. Here's a definition that comes from the IEEE Glossary of Software Engineering Terms. Error, okay, which a lot of people think of as synonymous with defect. But in fact, this definition of fault is probably more synonymous with defect. Okay, I'll try to get the difference between the two meanings here. A fault is some sort of a thing that is wrong with the work product. Okay, it's a flaw in the work product. Now, more commonly we use the word defect, but the IEEE glossary doesn't use the word defect. They use the word fault. Now, the word defect is from this third reference, Dunn and Ullman. But so they define defect as either a fault or some sort of a discrepancy between the code and documentation. I like this, that results in mischief in, in the testing, installation, maintenance, and use of the software. Okay, so I will tend to use the word defect synonymously with fault. I really prefer the word defect to fault. But you'll see both terms used. But unfortunately, sometimes you see the word error used in the same sort of a synonym with defect or fault, and it's not. Okay? So this distinction here, a fault, or as far as I'm concerned, a defect, is something that is wrong with the work product. Okay? Where did these defects get into the work product? We put them there. Okay? It's because software is a human intellectual endeavor, and humans make mistakes. The problem is we can't automate the construction of software because software development is more like design than it is construction. Right? So for example, automobile construction, well, once they get to the assembly line, all of the design has been done, and basically they're just putting the cars together. A lot of that can be automated. But the hard part about cars is designing the assembly line and designing the cars, and that cannot be automated. Okay, software construction, software development, programming cannot be automated any more than car design can be automated, or building architecture and design can be automated. Okay? Anything. These all involve creative work that involves and it can't be automated. It's intellectual power. All right, so software development cannot be automated, so you cannot prevent defects by automating the software construction process, the software design and coding process. So we make mistakes when we produce software. I mean, the closest we can come to automation, as we talked about before when we were talking about reuse, is, well, we could build software out of components, out of reusable, trusted, tested components, right? Thereby minimizing the chance of injecting defects because we minimize the number of lines of code we actually have to handcraft. Okay. That said, software development is largely a human intellectual endeavor. And anytime we have to write software, we risk injecting defects in that work product. Okay, so those faults or defects are flaws in the work product. These are things that are wrong, and we have to find them and fix them. Okay, now what's an error? By the definition in the IEEE glossary, an error is some sort of a mistake that you make that leads to a defect. Okay? The error itself is not the defect. The error is something about your process that allowed you to make the mistake, or in some cases even forced you to make the mistake in the worst case. But an error is a mistake that you make in doing your job, and that mistake will lead to a defect. Okay? So for example, maybe the defect is a misspelled word in a document. Okay? The error that you made is you don't know the way to spell that word. So you think the word is spelled, some improper spelling, right? And so every time you use that word, you misspell it every place in the document. So you've made one error. That means the error is you don't know how to spell the word. Okay? But that error leads to multiple defects in the document. If you use that word, say 5 times in the document, and you're consistently misspelling it every time, then you would have 5 faults or 5 defects in the document, all because of that one error. Okay? So an error is something, it's either some knowledge that we're lacking or something about the process that we use. Maybe it's the tools that we use, but a lot of times it's the process that we use to develop software. In this case, we're talking about software development. Okay? That enables us, or in some cases forces us, to inject defects. Now, when you're talking about defect prevention, it's the errors that we're trying to prevent. Okay? We're trying to look at what are the errors that we make that lead to the defects. And that's the way to prevent the defects. Okay? So that's the difference between an error and a defect. An error is a mistake that we make in our process that allows us to inject the defects. The defects are the manifestations of the errors. Okay? A third definition here is failure. A failure is when you run the software that has the defects in it, and the defect manifests itself and the software fails. Okay? It does not run correctly. As a matter of fact, it may stop running, or certainly it will not it will not do compute the results in the proper manner, and you'll get either the software will not work at all, or it'll give you wrong results. Okay? That's a failure, and the failure occurs when the software is run when there are defects in the software. Now, if there are no defects in the software, you will not have failures. The software won't fail. Right? The software fails because there are defects in the software. Period. All right, there are some references of these terms where we found those terms. So I'll try to be consistent in using the word defect or fault, and when I'm talking about the actual flaws in the software, and I'll try to use the word error when I refer to something that's wrong with our process that allows us to make the defects. And I'll talk about failures when we're talking about, mainly when we're talking about testing. We're trying to make the software fail when we do testing. So we're trying to find the defects by running the software in such a way that the defects will manifest themselves as failures. Oh, by the way, if you have a piece of software and it has a defect in it, you can run that piece of software and the software may not fail. Right? The software you have to run the software, and that line of code that has the defect in it has to be executed first of all. But even then you may not get the failure, because the failure may only occur in a small percentage of the time that you run that line of code, that you execute that line of code. And the state of the computation has to be just right for the defect to actually manifest itself as a failure. And that's the real challenge of testing, is how to run the software so as to force it to fail. And that's really what we're trying to do in testing. We'll talk about testing later on. We might categorize defects either based on a calculation of when in the software development process the defect was introduced into the work product. Okay, maybe by phase. So we could say, well, it's a requirements defect, or it's a design defect, or it's a coding defect. Now, a requirements defect If it remains in the software until you get to coding and testing, man, that is expensive to fix, as we recall from our discussions earlier. Right? It's an exponential growth rate in the cost to fix defects. So we'd like to find these defects as soon as we could. And that was the main sort of point when we were talking about reviews and walkthroughs and inspections and things. So we could categorize the defect based on when it was introduced. And sort of, we could say, well, it's a design defect or whatever. Or you could talk about the defect or categorize the defect. You find a defect and you can categorize it based on one of these generic categories like computational defect or logic or I/O or data, things like that. Now, let's back up. Why do we need to characterize the defects? What benefit does it have if we characterize the defect? I mean, after all, our tendency is that when we find a defect, we fix it and we'd like to forget it. We'd like to sweep it under the carpet and not even remember that we made the defect, right? That would be our tendency. The problem here is, as Santayana said, George Santayana said, those who do not remember history are forced to repeat it, or something of that nature. Right? So if we don't remember our defects, then we're very likely to make the same mistake in the future. So we would like to remember our defects and catalog them and characterize them and study the defects. Basically what we're trying to do is we're trying to find out what was the error that we made to lead to the defect. Because now if we say, well, how can I prevent that error in the future and avoid making that same defect a lot of times? Okay, so that's why we might want to characterize the defect and learn as much about it, what kind of defect it is, and why we made the defect, and therefore maybe we can prevent the defect. That's the whole thing here. So preventing defects is probably the most cost-effective way of assuring high quality. It's anything that we can do to change our process to avoid being able to put defects in, then that's probably cheaper than it is, not doing anything and then having to find the defects and fix them. That's getting expensive, and as we saw, it gets really expensive if you wait a long time before you find the defects and try to fix it. Okay, so what kind of things can we do to prevent the defects? Well, first of all, standards. Why do you have standards? Well, organizations have standards because they are proven best practices. They are proven techniques and processes and procedures that are proven to produce good quality work. And if you're following a set of standards, then you're less likely to inject defects in your work product. Okay? Software engineering methods, everything we talked about up to this point in the class, things like doing requirements and analysis and design and so forth, using programming languages effectively and things like that, doing reviews. Those are all software engineering methods and methodologies, techniques that will help in preventing defects. Languages, I talked about this before when we were talking about languages and compilers. Rather than using a language for which the compiler cannot check for certain classes of mistakes, let's use a language that allows the compiler to catch mistakes that people typically make. An example, Fortran is not a very good language for writing software, doing software engineering, because you can make a mistake in a Fortran program and the compiler will not be able to check that and catch that mistake. An example is on a subprogram call in a Fortran program. You can put whatever parameters you want in that subprogram call. The subprogram that you're calling is separately compiled by another Fortran compiler, and so the header on the procedure that you're calling, the subprogram that you're calling, when you compile that, it could have a totally different parameter list from the one that you're using when you invoke it, and the compiler can't check the interfaces. So you can pass total garbage to the procedure, the subprogram, and then when you put all these pieces together and try to test it, then you get all this mischief because you have mismatched parameter lists. The compiler can't check that. You have to test for that. You have to inspect and do reviews and things in order to find those kinds of mistakes. Right? A language like Java and languages that we have today the compiler will check all those interfaces for you, and it won't let you compile a program if you're passing the wrong kind of parameters to a procedure. Right? So that's an example of letting the compiler do some of the checking. There's a whole class of errors that Fortran programmers make like that the compiler and tools cannot catch, but you have to catch them either in inspections or probably in testing, and it gets very expensive to do that. Okay, so if we can prevent the defects by using a high-level language and a compiler, a good compiler, and maybe some good tools for catching those kinds of mistakes, that would be a good way, a cost-effective way of preventing the defect in the first place, so you never have to find it and fix it. Formal proofs of correctness could be done. Somerville, in his book, talks about formal software development, formal proofs of correctness, and things like that. I invite you to read. You can Google formal proofs of correctness if you want to learn more about it. I'm not going to spend any more time on formal software development here in this course, but that is a big area of investigation, and some people are actually able to do formal mathematical proofs of correctness on their software. We don't see that in actual practice very often. There may be some very special kinds of, maybe the kernel of an operating system that has to be secure. You might find the requirement to do a formal proof of correctness on that. It's kind of hard to do. I mean, takes a lot of effort to do a formal proof of correctness, and unfortunately, the state of the art of formal proofs is that it's probably more error prone to do the proof of correctness than it is to write the software in the first place. So we're not there yet, and we may need some tools and other notations to help us do that. Prototyping. We talked about prototyping way early in the class. And the benefit of doing a prototype, obviously, is that you get the software, your idea of the solution out in front of the stakeholders, in front of the customers and users, and let them see what they're getting very early. And if you're developing something, if you have a wrong idea about what they want, then you will get that feedback very early on. And so it'll prevent having building software that is not what the customer wants. I mean, that's remember the definition of software quality, building something that the customer needs and wants. Well, if you build a prototype and show it to them and get feedback on that, then you can prevent building something that they don't want or need. This continuous process improvement. This is a way to achieve quality in the future. So anytime you find an improvement to your process to prevent defects, then you change the process. You formally change the process. You document it. Now you can do this through redocumenting the process, changing the description of your process, or maybe through checklists. Right? So you have all these checklists as you're doing things. You check off the checklist, or as you're reviewing things, you can use a checklist of things to look for. Okay, so, and specifically, anytime you find a defect, what you ought to do is figure out what was the error that we made that led to that defect, and then say, well, what can we do to change our process to prevent us from making that error in the future, therefore preventing a large number of defects in the future. So we were looking to continually maintain our process to add things to it to prevent making the errors that lead to the defects. Well, okay, suppose you've done all these things that you can to prevent defects and they still get in there, right? Because we're humans, we make mistakes. All right, so we have to find the defects. Well, we talked about reviews, we talked about peer reviews, talked about pair programming, talked about walkthroughs, formal inspections. You can also do testing. We'll talk about testing later on. And this last bullet here, defect reporting. When you find a defect, we talked about this just a couple of minutes ago, when you find a defect, our tendency is to fix it and then forget it. But really we should report the defect, we should track the defects, because this is a way for us to modify our process, to look at the defects that we're making and figure out why we're making them. Look for the errors that we're making and then change our process. So it is very helpful to report these defects. I mean, as painful as it might seem, to celebrate these defects. I don't. There's nothing that we should be celebrating exactly because we made a mistake, but what we should do is we should record the defects and then investigate why we're making those defects and modify our process accordingly. And then after you find the defect, then obviously you have to remove the defect. Now, when you remove a defect, you're changing the product. Right? Anytime you change the product, now you've got a new configuration. We have to do what is called configuration management. All right? So every time, so we break our product up into pieces, into components. And a set of components with known versions is called a baseline. Right? A baseline is a known configuration of all the components at particular version levels. Now, if I change the one component in that, okay, now that component has a new version. So it's a delta to the baseline. So I take this known configuration and I change a couple of components. Now those are deltas to the baseline, little changes to the baseline. Anytime I change a component that is under baseline control, under configuration management control, I should do this in sort of the sunshine. I should do this overtly. And what you don't want to have happen is somebody to sneak into the library and modify a component unbeknownst to anybody else in the project. Okay, so any changes to any of the components should be done in a formal way through a formal change control process. Usually this involves something called a change control board, a group of people. This is people. This is not automated. This is a group of people that actually you have a proposal to change a component, right? And you submit this to the change control board and they approve it or not. I mean, they might not approve it because they'll say, well, wait a minute, if I change that component, all sorts of other stuff will break. And so they may, in fact, not approve it. Generally speaking, though, the change does get approved, but it's noted, it's documented, that formal change request is documented, it's stored in a repository, and then you modify the component. Now, that component is a new version. The configuration management people keep track of each version of each component. So every time a component is changed, you have a new version. So some components might have 4 or 5 or 6 versions over time. And the configuration management people have to keep track of all those versions of all the components and then figure out, well, which versions of which components go into a particular configuration. That's the whole challenge of configuration management. It's a big job. Regression testing we talked about before, right? When you change a component or change some software, then you test the change that you just made, but then you have to retest other stuff, because you might have actually inadvertently changed something so that there's this ripple effect. And so you changed one thing in your system, and that might have an effect on something else that you didn't modify, but it no longer works now. Right? So you need to test the new stuff that you add, but during maintenance, for example, but you also have to regression test. You have to rerun test cases on stuff that used to work and make sure it still works. And that's called regression testing. And it all has to do with finding these ripples from the ripple effect. The ripple effect means I change one thing in my software, and now something else in the software that used to work now doesn't work anymore. That's called a ripple effect. Really, we'd like to minimize those ripple effects. The main way that you can do that, the main way to minimize these ripple effects is modular software construction and maintaining and modifying just the inside of a module. Remember the encapsulation idea? If you change just the inside of a module, the hidden part, then that change is not visible outside the module. It doesn't affect the other modules. So that is a way to prevent these ripple effects. Modify just the inside details, implementation part of a module. The change then should not go beyond that module itself.